We have a question here associated with Newton's law of cooling, and we know that the rate at which a body cools is proportional to the difference in temperature between the body and the ambient temperature. Now what we want to do is start reading the problem and symbolize the given information. For example, we know the body was found in a closed room whose temperature was a constant 70 degrees Fahrenheit. So this means that the temperature of the surroundings, also known as the ambient temperature, was a constant 70. We read on and we know that at the time of discovery, which is denoted as T sub 1, the temperature was 85 degrees. So what we can say is that the temperature at a time of T sub 1 was equal to 85 degrees. Reading on, we know that 1 hour later, the temperature of the body was 80 degrees. So symbolically, we would say that the temperature T, and then now the time is going to be the T sub 1 plus 1, because it's 1 hour after the body was discovered. That temperature was 80 degrees. And then finally, we read that at a time of 0, the core temperature of the body was 98.6. So above here, we can say that the temperature at time 0 was equal to 98.6. And then finally, we want to get a sense of what we're trying to solve for. It says determine how many hours elapsed before the body was found. So we are looking for T sub 1 because that is the time that the body was discovered. So that's how much time elapsed before it was found. That is our goal right now, and we begin to solve that goal by trying to plug into the differential equation. Now we have dt over d lowercase t. Remember, uppercase t is temperature, lowercase t is time. This is equal to k times t minus the ambient temperature, which was 70. So we can get a little progress by plugging in that 70. But what we really want to do is rearrange this equation. We want to isolate the temperature variable on one side and then isolate the time variable on the other side. This is known as separation of variables. So for instance, we could do that by multiplying both sides of this equation by 1 over t minus 70 so that we can cancel it out on the right-hand side. And then we'll make a little bit of room here so we can multiply the left-hand side also by 1 over t minus 70. So it'll look like the following. Now we can clean up the right-hand side. So right now we just have k on that side, and then we need to multiply both sides by dt. We'll kind of squeeze it in right here. And that will cancel the dt out on the left-hand side. So now we've separated variables very effectively here. We have the temperature on one side and the time on the other side. After separating the variables, we need to next integrate both sides of this equation. Now hopefully from a calculus course, you know that the integral of 1 over t minus 70 is the natural log of the quantity t minus 70. And then on the other side, you're integrating a constant with respect to t, so that integral is just the constant multiplied by t. And then we have to add an arbitrary constant of integration. Now we're going to actually solve for that capital C right now, because recall that the temperature at a time 0 was 98.6 degrees. So what does this mean? Well, it means that for capital T, we can plug in 98.6, and for lowercase t, we can plug in 0. So of course, on the left-hand side, we just now have the natural log of 28.6. And conveniently on the right side, this goes to 0. So look at that. We have the arbitrary constant c. So what we'll do is take this equation, which was sort of the solution to the differential equation, and we will plug in for c the natural log of 28.6. Okay, this is great. We have the constant of integration, capital C, solved for, but now we want to solve the equation for the actual temperature of the body as a function of time. So in other words, we're going to try to solve for capital T. And to do that, we would need to cancel out the natural log on the left side. Now, of course, we can raise e to both sides of the equation because e and the natural log are inverse functions. They cancel each other out when applied on each other. So now we have t minus 70 is equal to this e to the power of kt plus the natural log of 28.6. Let's talk about how to simplify the right-hand side. We'll take a brief aside. Recall that when you have, let's say, e to the x plus y, you can rewrite that as e to the x multiplied by e to the y. So using that property of exponents, we can rewrite the right-hand side as e to the kt multiplied by e to the natural log of 28.6. Now that's pretty nifty because once again we have an e and a natural log as inverse functions. They cancel each other out. So we can write this as t minus 70 is equal to e to the kt times 28.6. And then we can just reverse the order on the right-hand side and call it 28.6 times e to the kt. So this is looking pretty nifty. We could actually solve for t, but let's consider some of the other given information for just a moment. And there is that information that we haven't used yet, and it might actually be useful to begin plugging that information in. So for instance, if we look up here, we have T sub 1, and then we have a temperature of 85. So what that means is that we can take the 85, plug it in right here, and then for the time, the little t on the other side, we can actually plug in T sub 1. So you're going to have K times T sub 1. And yes, there are two unknowns there. We'll take care of that momentarily. And then for the other information, we have a time of T sub 1 plus 1, and then a temperature of 80. So similarly, then, we can write down that 80 minus 70 equals 28.6 e to the k times, and then this time is kind of funny, it's T sub 1 plus 1. Now, let's simplify these a little bit. So going back to the first equation, we have 85 minus 70, so we have 15 is equal to the right-hand side. And then over here we have 10 is equal to the right-hand side. Now it turns out that it's going to be strategic for us to write these two equations kind of stacked on top of one another. So we're going to take this equation, and then we're going to kind of stack it on top of this equation right here. Let's go ahead and do that. There we go. Now the reason we stack these equations is because it allows us to divide them. So if we divide 15 by 10, then of course we'll get 1.5. When we divide the right-hand sides, the 28.6 divided by itself is going to be 1. And now we have to be careful because now we are dividing these two exponential terms. Just another rule to keep in mind that when you're dividing e to the power of m by e to the power of n, then you would have e to the power of m minus n. So in other words, on the right-hand side, we're going to have e to the power of k times t sub 1 minus k times the quantity t sub 1 plus 1. Now that looks a little intimidating, but it actually will simplify pretty neatly because we can distribute this minus k. So let's take a look at what we have when doing that. We're going to have e to the power of k times t sub 1 minus k times t sub 1, and then minus k. Now you're noticing that's pretty nifty because kt1 minus kt1 cancels. So that's all just 0, and 0 minus k is negative k. And this is really nice because this allows us to solve for that proportionality constant k. To do that, we will take the natural log of both sides. And then we have a property of logarithms that allows us to pull that exponent as a coefficient. So it becomes negative k times the ln of e, which is pretty cool because the natural log of e is just 1. So negative k times ln of e is just negative k. And then we divide both sides by negative 1, and we end up with the value of k. Now on a calculator, that's going to come out to approximately negative 0.405. That is the approximate value of k. That's nice because now we can use that k to solve for t sub 1. We go back and we can pick a couple of different equations, but perhaps the easiest one to select would be this equation right here. So let's recopy that below. And then into that equation, we can take our value of k and substitute that in. And now you can see we are in business here. We can easily solve this for t sub 1 by dividing both sides of the equation by 28.6. We will then take the natural log of both sides. So if we do that, that will allow us to cancel out the e on the right-hand side, just like we did earlier. And then finally, just divide both sides by the negative 0.405. And when you punch that into your calculator, you will find that t sub 1 is equaling about 1.59 hours. That is the correct answer to the question. We can go back and just make sure we remember what the question actually was. Remember, we were looking for t sub 1. We were looking for how many hours had elapsed before the body was found. So that body was sitting there for about 1.59 hours before it was discovered. Thank you for taking the time to watch the video. If you're interested in making a small donation to my cause, I'd greatly appreciate it, but please, of course, do not feel obligated to do so.